This is the screen recording for Chapter 17 homework. This dealt with diffraction and interference patterns. Problem number 1 was asking you to figure out how long it took something to go through glass with an index refraction of 1.5. So the key thing is understanding how light slows down, or electromagnetic waves slow down. So they slow down by a factor of the index of refraction. So the speed through glass is 2 times 10 to the 8th meters per second. Then you can simply use the speed is equal to change in position over change in time to figure out how long it takes. For number 4, the reason, or due to the fact that light slows down when going through different materials, affects the wavelength of those light waves as well. So it does not affect the frequency. The frequency of a wave is dependent on what makes the wave. The wavelength is dependent on what it's traveling through. So in this case, if you end up having known wavelengths of 670 and then a new wavelength of 420 nanometers, it means it's getting shorter as it's going to the new material, and therefore that means it's going slower. So the ratio of those two gives us the index of refraction, that's 1.595, and therefore we can use that index of refraction with this formula to determine how fast the speed of light is going in that new material. Then, since frequency doesn't change, we can use either F equals c over lambda or the velocity we calculated over the new lambda. Either one of those should give us the same answer because the ratio is the same number of waves passing per second. So that's about 4.5 times 10 to the 14th hertz. For number 11, we'd see that the wavelength is 6 times 10 to the negative 7th meters. Use the diffraction formula, and if we have a new wavelength that's only 2/3 that amount, that means that since this side is only 2/3 of the amount, this side would also be 2/3 the amount. So the sine theta would change. So therefore the fringes are going to end up being closer together. So instead of 1.8 millimeters apart, they'd be 1.2 millimeters apart. For number 17, we're trying to find the distance. We are told that we have got 1,000 slits per centimeter. I'm going to convert that to slits per meter and figure out meters per slit. So that's the D, the distance between any two openings, and diffraction grating. And remember, diffraction can be caused by either by a grating where light passes through or a reflection off of a ridged surface. So that's how we see some neat reflections off of CDs and DVDs for anyone who still plays those. At any rate, if we know the wavelength, which was given, and we know that distance, then we can go back to our general diffraction formula, go back, rearrange to solve for the sine of theta. Inverse sine of all this stuff would give us the angle. That's 3.15 degrees. If we're looking at the second order wavelength, or the location of that, that would actually be 6.31 degrees. So almost double, which makes sense for a small angle. Looking at problem 25, and I was going to do 27, I screwed up. So for 25, we're looking at constructive interference. So it flips at both surfaces here, on the oil, which has an index of refraction 1.25, and on the water, which has an index of refraction 1.33. Why does it do that? Because each of these materials is more dense than the surface or the material it's coming from. So 1.25 is greater than air, which is 1.00. Water is greater than oil. So since they both flip, and this extra distance down plus up here, that would end up being a path length difference of, let's see here. I think it was asking about, I hope it was asking about destructive interference, yeah. So if they would be in phase since both of these flip, we would need a half wavelength path difference for destructive interference. So therefore, this thickness – 200 nanometers. Okay. I'm not confident on that. I might have to go back and look at that for just a minute. Actually, now I think it's constructive interference. Darn it. Okay. So this plus this total, you know what? I'm going to go look. So give me a second. Sorry about that. Chapter 17. 125. So it says a very thin film of oil film on water. It's the thinnest film that produces a strong reflection of green light. Okay, so we want constructive interference. So what that means is this path difference would be one wavelength, and the thickness would be half a wavelength. So I will correct that in just a few minutes. The reason it's 200 instead of 250 is because the index of refraction of oil is 1.25. The wavelength is smaller. I don't think the AP will ever ask you that. So it's for number 27 that it's asking about destructive interference, I think. So it's a silicon solar cell located with a layer or coated with a layer of silicon dioxide. What's the minimum coating that minimizes the reflection? So we want destructive interference through the coating, which is 1.45. So this flips, this flips. Therefore, twice the thickness, down plus up. We would want to be half a wavelength to be out of phase. So therefore, the thickness would be a quarter of a wavelength. So that's a quarter of this in that material, which is 483 nanometers, 121 nanometers thick. 48 tells you the spacing between the fringes here is 6 centimeters. That's 0.06 meters. This distance is 2.5. We're going to use inverse tangent to get that angle. Go back to the d sine theta to get that distance between the slits. So that's 2.2 times 10 to the negative fourth meters. 57, again, convert everything to standard units. 2 times 10 to the negative 6 meters is the distance between the slits there. Gives us an angle. End up figuring out that m theta, or m lambda, is equal to this. For the other angle, m lambda is equal to this. So this ratio is 4 to 3, so these would have to be the third and fourth order lines. So if they're the third and fourth order line, I could say the third order line is this amount of wavelength, m times lambda. Then lambda by itself would be this divided by 3, which is 4.77 times 10 to the negative 7th meters. So I'm going to go back up here and say this better. Constructive So I'm going to put this around. Nope. Okay, so I think that's good, and I think I'm going to quit out of this, and that is the pencast.